Hello guys, this would be the last part of the discussion for the finals period for the IC or integrated circuits, and this would focus on the computational aspects for the design of the 5i5 timer, and also we'll have a few examples of getting signal to noise ratio. Now, last video we discussed some design aspects of a 5i5 timer in terms of the three types of multivibrator. So we had a design for both monostable, astable, and the bistable multivibrator as well. Now, among the three, we don't actually need to compute or calculate the design for a bistable multivibrator as it is independent of the passive devices connected to the circuit. But as for monostable and monostable and astable multivibrator, we are actually uh, bound by the passive devices connected to our three main pins, which is the threshold, the trigger, and the reset. Okay? We've already covered a bit of how those passive devices, the resistor and the capacitor, affect the duration of the output. So for now, we'll be looking into the design for an astable multivibrator, and let's take a look on how it is affected by the design and also the value of the passive devices connected to it. So we're already done with, so this is just another view of the astable multivibrator. So we won't be going into detail for that. So what we want to affect or to change that affects the output, the blinking rate of this LED would be R1, R2, and C1. C2 here connected to the control pin as discussed yesterday is for smoothing out possible fluctuations in the source voltage. The R3 here is used as a limiting resistor to protect our LED from possible burnout. So with that being said, let's take a look at the main factor that affects the duration or albeit the blinking rate of our LED connected to our pin 3, which is the output. So for the period, so period being the duration of one cycle. Okay? So we've discussed that from the uh, second to the last or the prior video, that one period is the duration from one point of the rising edge to another point of the rising edge from the next cycle or the next two falling edges. So the period is divided into two. The duration or the period when the output is high and the duration of when the output is low, denoted by T high or T sub high and T sub low. And the period is actually the sum of the two. So the period would be the sum of T sub high and T sub low. Now, T sub high or the duration of the output at a high state is actually affected by the three passive devices. So it's affected by R1, R2, and C1. So T sub high is actually 0.693 multiplied by the sum of R1 and R2, then multiplied by the value of C1. While T sub low is only affected by R2 and C1, not R1. So it's just the product of 0.693, R2, and C1. Then we add those two together. So shown here is how we could determine the formula or derive the formula coming from T high and T low. So doing a bit of algebra, we'd be able to determine that period would be equal to 0.693 R1 plus 2 R2 times C1. Now, frequency, for that matter, as with analog devices, frequency is the reciprocal of the period, so we just have to find its reciprocal and we'll be able to get its frequency. Now, the duty cycle pertains to the percentage of one cycle in which the output is at a high state compared to the total duration of one cycle. So with that being said, it would be the duration of the high state divided by the total duration times 100. We could plug in the data here or the formulas for T sub high and T sub low, and we could actually determine the duty cycle as the ratio of the sum of R1 and R2 and the sum of R1 times twice R2 multiplied by 100%. So let's take a look at an example here and let's try looking into using those formula. So here we go. So let me just minimize this a bit. So we are to okay, so adjusting it really won't work. There we go. So in our circuit diagram, the value of resistors R1 and R2 is 1 kilo ohm and 100 kilo ohm respectively. The value of capacitor C1 is 10 microfarad. So we are to find its period, frequency, and duty cycle. So for period, we were already given a formula. Well, we could try finding the duration for high and duration for low and then adding it together. But from the problem itself, it was not being asked. So we could use our derived formula as shown here, which is 0.693 R1 plus 2 R2 C1. So that will be T equal to 0.693 multiplied by our R1 plus 2R2 times C1. So from our given, R1 is 1K, R2 is 100K. Oops. So 1 kilo ohms plus 2 times R2, so that would be twice the 100 kilo ohm. Let's just copy that. Multiplied by C1. Let's remove this. I already know what it means, even without the asterisk. So C1 was slated at 10 microfarad. Okay, so 10 microfarad. Okay. So the duration would now be, so we have, I'd like to do this first. So this would be 200K plus 1, that would be 201 kilo ohms. That would be exponent 3. Well, then multiply it with 10 microfarad. Micro is negative 6. And then we multiply it by 0.693. So which is equal to 1.39 seconds. Okay, let's confirm that. So we have 202 kilo ohms, 201 exponent 3, okay, multiplied by 10 exponent negative 6 multiplied by 0.693. So we have 1.39 seconds. Now, we have our period. It's time to find frequency. So frequency would just be 1 divided, or the reciprocal of our period. So that would mean our frequency would be, where is that? Yeah, here we go. The reciprocal of our answer, which is 717.9 91 millihertz. Okay. That is quite rare. Then our duty cycle, as mentioned, is equal to the ratio of T high, or the duration of when the cycle is at the high state, and the total duration of the cycle. So we don't have T high. I don't want to compute for that as it was not being asked. So we just use our uh, derived formula, in which R1, in which is equal to, let's use this. So R1 plus R2, wait, R1 R2 divided by, nope, let me just go, thank you, 2R2, there we go, times 100%. Okay. So that would give us around, our R1 would be 101, because our R1 is 1K. So we have this. Let's just use this. It's the same. Wait. Let me use this one first. So we have 1 kilo ohm plus 100 kilo ohm divided by 1 kilo ohm plus 200 kilo ohms. Times 100%. So our duty cycle would now be 101K over 201K. 101 kilo ohm divided by 201 kilo ohm. Of course, I forgot that. Let's not forget the times 100 here. So Our duty cycle would now be 101 divided by 201. Because they have both have kilo ohms, we don't need to put in the kilos together. Then we'll be multiplying this by 100. So we have around 50.25, almost 50% duty cycle. So it's almost the time that it is at a high state and a low state are almost equal. So next, let's look at our. So I'll be leaving the second example for you guys and take a crack at it and check if you'll be able to understand following the discussion that I just did. As for the signal to noise ratio, it's actually quite simple, as it's almost like calculating for gain, especially if we're going to put it into decibels. But of course, as mentioned from the first lecture, we won't be using output over input, but rather uh, signal noise, or no, sorry, signal power, signal voltage, or signal current over noise power, current, or voltage. When you're going to compute for signal to noise ratio, you can only compare power with power, voltage with voltage, and current with current. So if for instance, a signal power is given and then voltage or noise voltage is given, we won't be able to use those two to be able to compute signal to noise ratio as it is. We need other values to be able to derive our correct information. Now, with that being said, just like what we did with gain and loss, if we're going to show it in decibels or represent it in decibels, if we're going to use power, so where we have the signal power and the noise power, where you're going to use 10 logarithm of signal power and noise over noise power. If it's voltage or current, we use 20 logarithm of signal over noise. So we have a short example here. Let's take a look at this. So a signal of 2.5 volts RMS, or root mean square, is corrupted by 10 millivolts RMS of noise in a particular circuit. What is the signal to noise ratio at this point? So it's actually quite straightforward. The given problem is in voltage, so that means our signal to noise ratio in decibels would be 20 logarithm of signal voltage over noise voltage. Okay. So we have our signal voltage, as mentioned, as 2.5 volts RMS. Another word of caution, when dealing with voltages, you have to make sure that we are talking about the same type of voltage. VRMS is different from DC voltage, from AC voltage. So we have to make sure that we are, if the noise voltage is in RMS, we should be comparing it with the RMS of the signal voltage as well. If it's a DC voltage, you have to be both DC voltage, so on and so forth. Going back, our noise voltage is 10 millivolts RMS. So our signal to noise ratio would now be 2.5 divided by 10 millivolt, then logarithm multiplied by 20. So we have around 47.96, almost 48. So this is, well, the main way to compare signal to noise ratio is compare its value in decibels. So if a certain stage in a system or in a certain stage in a communication system has a high signal to noise ratio, then that means that system or that part of the system is actually quite good. Well, normally in the communication systems, we focus our attention on the one with the lowest signal to noise ratio. In other literature or in most designs as well, we have to check the signal to noise ratio of the first stage, because any noise coming in on the first stage would get amplified at the later stages. So we have to make sure that we have a very high signal to noise ratio at the first stage of our communication system. Because if it has a low signal to noise ratio, meaning it already has high noise to begin with, and normally in communication systems it goes to several amplifiers, the noise gets amplified as well. Okay. In the absence of any noise cancelling circuits or noise minimizing circuits. Again, we just have to remember, if the power is the one given, we change this to 10 logarithm. Okay, and that's it. If you have any other questions with regards to this lesson, please feel free to comment or message me. And good luck to your exams. And hopefully I was able to impart some knowledge with you guys. Thank you very much and keep safe.